Usain Bolt does teach everything you need to know about calculus. Let's see. So here we've got a race. This is from 2009 World Championships. And there's Usain Bolt running very fast. Set a new world record. So if somebody's running as fast as they can, like thinking like him, well, I don't know. If your strategy was, I want to run as fast as I can, you think like, okay, I want to be able to run at my fastest speed, constant speed the whole time. Are you trying to be speeding up as much as you can? Well, maybe you think, well, if I'm speeding up, I should have been running faster earlier because I obviously have a faster speed. But it's a very short race. So there's not a whole lot of time to speed up, slow down, whatever. Let me show you a graph based on data from this. And let me get this to not keep playing things. So based on data from that race, because tracks are high-tech and they have position, they can locate people at any point in time, plus you can actually use videos and stuff to determine positions and therefore speeds at various points in time. So in this graph here, I'm going to show a graph of y equals f of t, where f of t is Usain's distance from the start measured in meters. That was a 100-meter race. And t is the elapsed time in seconds. And his world record was 9.58 seconds for 100 meters. So this is almost real time here. But you can see this graph of time versus position. I'll just pause it kind of in the middle. This beginning part, what about the beginning part lets you know that he's going slower than he is at this later part here? Just visually. Yeah, it's not as steep. And you can see like later on, this looks kind of straight line-ish. The beginning part is definitely curved, but whatever it is, it's certainly not as steep here as there. Now steepness, slope, is that rate of change computation we've talked about before. And this isn't a straight line. In fact, I have an equation up here. It's actually a model to fit the data. Fifth degree polynomial equation does go through the origin, but this is modeled to fit data. You can see it fifth degree, but with some really small coefficients, means it's going to look kind of linear for a while. It's not going to curve up and down too much, and curving down in this case would be super weird. But between 0 and like 9.58 seconds, he's certainly going. He's not going uphill. He's not going faster and faster, maybe, but looks like at the beginning, this curving up like that looks like, oh, his speed is getting faster. This is steepness. The number of the vertical measurement here is meters, and the horizontal is time in seconds. So we've got more meters in the same amount of seconds, more distance in the same amount of time if I look later as opposed to earlier. So that would indicate, oh, faster. So that's why this steeper indicates faster. And this isn't a straight line, but if you look later on, it looks very line-like, maybe from this section here. And actually on Thursday, we're going to play around with this. I'm going to give you a copy of this GC file. We're going to do some other stuff with it and analyze speed between lots of different points and see what's going on with that. But if I wanted to find his speed, the rate of change of distance to time, so that meters per second sort of speed, we could think about that by looking at various points in this graph, but this is the whole thing, and most of it looks fairly linear. And so the reason that's important is because what we were talking about for the first couple weeks of class, this idea of constant rate of change doesn't only help us in situations where we have exactly constant rates all the time for whatever long time period or long input period, like the barrel of water. Well, it's always going to be 8.3 pounds per gallon. It doesn't change when you add more gallons to be more pounds per gallon or fewer pounds per gallon. The only thing that would change that is like elevation or a different planet or something like that. So in any case, you don't have to have constant rate of change all the time to use our tools of constant rate of change because, well, even within things that aren't constant rates all the time, there are moments, sometimes longer, sometimes shorter, where we have approximate constant rate of change, and we can use the ideas of that, dy equals mdx, to compute what's accomplished because of a rate, maybe not just using one rate for a long time, but breaking this up into, okay, well, what rate was he traveling at around 3 seconds into the race, around 4 seconds into the race, around 5 seconds into the race? You could break it up nice and evenly every second. And if you knew those speeds then, even without, this is a distance graph, if you knew how fast he was going around 3 seconds into the race, you could see how far he traveled during, maybe use that speed for a second, or maybe only use it for 1/10 of a second. But we could use these approximated constant rate of changes to generate what happens because of that. If we know information about rates of change, whether they're constant or just we imagine them to be constant for small periods of time, we can generate what happens because of that afterward, or vice versa. If we know how much has happened, how far he ran, we can estimate constant speeds at various points in time from that. Just kind of like you're driving down the road, your speedometer tells you how fast you're driving, but you don't have to drive at a constant rate for it to give you a number. It just changes every so often. And it is based on ratios of things, actually, and that's why changing your wheel sizes can mess up your speedometer. It's based on axles turning and how large your wheels are supposed to be, how far you would go down the road. It's not actually like measuring how fast trees are approaching or anything magic like that. Now, some of those like remote control sort of like driverless cars, they have some other things that are going on to measure things. They do pay attention to other things, but the speedometer is basically, well, it's computerized now, but it's based on mechanical means of axles turning and wheel radius. So let's take a look at just this graph. I want to zoom in a little bit just to tell you kind of what I mean by this, about this approximate constant rate of change. So let me zoom in around 4 minutes here. I'm just going to do, if you do have graphs, this is something we'll do on Thursday, but if you hold down the shift button and then click, you can drag and zoom in on a little box like that and then just let go. So here we are around 4 seconds into the race. Still looks pretty much like a constant rate. What I'm going to do is figure out between time 3.9, or as close as I can get to it, there, and 4.1, that 0.2 seconds, what his speed seems to be, or this average rate of change over a small interval. So if you went 9.58, if it took 9.58 seconds to go 100 meters, I know what his average speed over the full race was. Just do meters traveled divided by seconds traveled, and you get meters per second. And I don't know what that number is off the top of my head. Let me do this real quick. Here. 100 meters divided by 9.58 seconds. Oops. Divided by, there we go, 9.58 seconds. That's about 10.43 meters per second on average would get him to go that distance in the allotted amount of time. Now, as we saw though, he was going slow at the beginning. In fact, he started from a standstill. That's how track meets work. And so he must have sped up, which means at some point during the race he was going faster than this, because at some points we know he was going slower. That's why it's an average. It's in between the highest and the lowest, but in a way such that if he were able to travel at precisely this speed for 9.58 seconds, he would have traveled 100 meters. So back to this. If I wanted to compute a speed, we were talking about the slope of this. So let me just, I think I can get this to work on this aspect today. Maybe not a keynote, but so at this point, 3.9, 31 point, I'm just going to round this to 31.44. So I've got a point here, 3.9, comma, 31.44. And this is at 3.9 seconds into the race, he was 31.44 meters from the starting line. By the time he was farther into the race, let me say this 4.1 seconds, if I can click on that. There we go, 4.1 seconds. Here's 33.73, just rounding again, meters into the race. So during that 0.2 seconds, he traveled, let's see, a little over 2 meters, 2.29, if I can subtract properly. 2.29 meters, and he was going forward the whole time because he was trying to win. So this is 2.29 meters net change, but also all forward in 0.2 seconds. So if we do meters divided by seconds, we'll get his speed, which you can maybe see is going to be close to that number that we had before. 2.2 goes into that, let's see, 11.45 times. I mean, I could pull up GC again, but dividing by 0.2 is not too hard. If I can do this, 11.45, yeah. So 11.45 meters per second during that 0.2 second interval. Now that's faster than the average speed of 10.4 something that I worked out before, but that's good because I bet if we were to do this same sort of computation near the beginning, that it would come out to be a lot less than 11.45 meters per second. Now, what I do want to do is hit this zoomed in here. This looks like a straight line. It's not exactly a straight line. I know it's not a straight line because we know it's a 5th degree polynomial curve, just with really small coefficients on some of the higher power terms. But thinking about that, if I were to look at another point here at, make this clicking, at 4. Let's see if I can get it to be exactly 4. So I've got this point 4 comma 32.58. I'm guessing if you check the slope between, ooh, I didn't even make a mark there. There we go. I'll just move this out of the way. Let's see. I'm guessing if you found the slope between the right 2 and the left 2 points and versus the first and the third, they're not all going to be exactly the same. If this were exactly a straight line, any 2 points you pick and calculate the slope, meters per second for this example, between would come out exactly the same. These will probably be close because I see, like, this is zoomed in fairly close to this graph. This is not a lot of time going by. This is 0.2 of a second, which is a big difference in terms of like winning an Olympic sprint race. 0.2 of a second is a huge difference. But just talking about, is he speeding up a lot during that time? Probably not. But we could figure out, is he, at this point, is he speeding up or slowing down? And we can look at, well, what's his speed during this first 1/10 of a second versus what's his speed during the second 1/10 of a second. Again, it's really an average rate of change because he's not going exactly the same speed during that interval, but it's pretty close. And we can see this by looking at different intervals and seeing that the values we get are all fairly similar to one another. So if you want to do this computation, we could find the slope for this segment, find the slope for that segment as if they are exactly line segments. Find that vertical divided by horizontal change. It's t dt versus df of t. I don't have a number for it. dt versus dy. That ratio. And they won't be exactly the same, but they'll be very close. And they're going to be very close to this 11.45. I'm guessing that the one just to the left is a little bit smaller and the one to the right is a little bit larger. But again, we'll play around and look at some of these patterns and these rates of change in his full graph tomorrow, or not tomorrow, Thursday. I'll have a worksheet for you. We'll spend time. I'll turn on the light so you can see better and everything. So I will post the worksheet in advance of class if you want to download it and look at it yourself on your computer. But it's really just let's do some computations, play around with GC, find some numbers, and we'll discuss the patterns and the numbers that we see and what they mean. Not just about Usain Bolt, but about calculus in general, because as I said, Usain Bolt will teach us all of calculus. No. So in any case, let's talk about some other aspects of measuring change in small amounts of time. Let's see, this one. All right, so here's the race we were just watching. Usain Bolt broke the all-time world record in the 100-meter sprint by finishing in 9.58 seconds. This was in 2009, but this record still stands as of now. We'll see if somebody breaks it in the near future. Who knows? But this question, which I already kind of posed this earlier, how fast did he run in meters per second? We could find that 10.43 something, but he's probably not running the same speed all the time. Obviously, at the beginning, he was not going anywhere. He can't, like, instantaneously jump from 0 to 10 point something meters per second and just then stay there. If he had the power to go from 0 to 10.43 meters per second speed in an instant, I would think he'd be able to increase his speed from there because he clearly has magical powers. But in any case, probably did not run at a constant speed the whole race. And in fact, we saw that graph didn't look like a constant speed. At the first couple seconds, definitely looked to be less steep visually, meaning lower ratio of meters to seconds. So I want to think about what this means, though, if we say a speed corresponding to a single time. So what would it mean that at 1 second after the start, he was running at 6.148 meters per second? If I zoomed in around there, we would have gotten this number. Well, we say that sort of thing all the time, like talking about driving somewhere, or if you're running someplace, how fast somebody's going, how fast a baseball pitch, whatever. But if we're talking about this race here, time going forward, if I want to know at 1 second after the start, he was running 6.148 meters per second. This picture is taken at 1 second after the start. Now, at 1 second after the start, at one point in time, he is in one spot. So it's a little bit difficult in reality. Like, we're used to saying these sorts of things. Like, well, oh, at this instant, at this point in time, he's going 6.148 meters per second. But if we're talking about literally one point in time, not letting any time go by, he isn't moving, just like he's not in a picture. Would you agree? Like, if you're really just talking about one point in time, there's no movement, so there can't be any speed. So we know what we mean when we say that sort of thing, but what it is actually kind of a complex concept. It's like, all right, well, I'm going this speed now. I assign a number to a single point in time, but really, in order to see that speed, you have to at least let a little bit of time go by. And normally there's a lot more that goes by, and so you're okay with talking about it as a single point. But if it was really a single point in time, nothing is changing. So I'm running as fast as he is. So that's cool. So instead of talking about a point in time or an instant in time, to kind of give the idea of, or to just help you remember to think about the fact that this has to happen, in order for something to have an amount of change happen, the things contributing to change have to be moving. We have to have variables that are varying. We can't just have a frozen instant. So if we use the word moment instead, we say, oh, just a moment, you usually mean, a few seconds or something. But we can talk about a moment in time, meaning just some small amount of time, not a specific, like, oh, moment stands for 0.1 seconds or anything specific like that, but just meaning a small amount of time. So if I imagine a small amount of time, or maybe even in this picture, they do look a bit blurry. Shutter speeds are what they are. And if you looked at the book about the cars and the blur and stuff, like, well, he must actually be moving. And in fact, he's moving faster than the camera was able to capture, because his arms are all blurry right now. And I know that his arms in reality aren't blurry, they're regular arms. So he must be moving, or this picture actually captured not a single instant, but a small moment of time in reality. It's just that it's hard to see because, well, we photographed it as if it all happened at the same time. That's how it works. but in reality we've captured a little bit of time, and that's why it's blurry. So in the moment of time, you say, oh, well, he's going at 6.148 meters per second. So if this represents, just to pick an easy number to deal with, 100th of a second was somehow shown in this picture, the blur that you see there would indicate, let's see, 0.06 meters worth of something, so 6 centimeters worth of motion in that 100th of a second. So, okay, that seems maybe reasonable. And you can even kind of say, oh yeah, that's why it's not a crisp, clear picture, because there was actually motion during the time that the camera was doing its job. So whether you have a physical film camera or a digital camera, it can only capture things so quickly. Digital ones can do a lot faster than the physical ones, physical like media film. But in any case there, you can, if you think about this as representing a moment in time instead of a single instant, it makes more sense to talk about speed and also to understand why it's blurry. Like, okay, so that's actually representing the motion that's going on. So thinking of a moment then, when I say this word moment, and you can use it to describe things too, think of it as a small amount of time or a small interval of values of whatever your independent variable is, and then whatever happens because of that independent variable changing a little would also be probably quite small, but obviously it depends on what the rate of change is from one to the other, from independent to dependent. So this moment is a small interval of values of the independent variable and its quantity that it's measuring. So we're going to use this symbol dx. We used it before, represents a change in x, but we're going to use this from now on. It'll just be to be able to apply this in any situations. We'll talk about it as just representative of small amounts of change in x, not just any amount of change. We could have, in our previous examples, used any amount of change, but we'll stick with small amounts of change. So a rate of change at a moment, or a rate of change in a moment, if you want to think of it that way, only exists if there's a small enough interval in which the rate of change is essentially constant. So this is just about every situation we've talked about. Thinking about the graph that we're just looking at, visually speaking, if you can zoom in a way so that it looks fairly much like a straight line, that you can't decipher the difference, and even if you do computations, the rates of change you compute come out to be about the same between 2 points of your choice, any 2 points, no matter whether they're extremely, extremely close together within that moment or maybe a little farther apart, 0.1 seconds, 0.2 seconds. That was a pretty small part of the race. But we can talk about that rate of change at a moment. In this example, it was speed at a moment, how fast he was running at a moment. If there's a small enough interval where that rate of change seems essentially constant, so whether it's by doing computations or by looking visually at a graph, there are lots of examples of graphs that don't have constant rates of change anywhere. Those are unpleasant things with very messy looking functions. There are many sorts of graphs that you've seen that have at least one moment, one spot in the graph where there isn't going to be a constant rate of change. Things like, let's doodle this on here. So if I had like absolute value graph, let's see if this is going to exit me out for a second, but let's see if it's going to play along today, just out of curiosity. So if I had like y equals absolute value of x, and I had something like this, obviously if it's just y equals absolute value of x, I know that the two sides to that are perfectly straight lines, even straighter than my picture shows, but zooming in around the vertex, which would be at 0, 0 if it's actually exactly this graph, no matter how close you zoom in, a corner is not going to turn into a straight line. It always has to, we've got a negative rate of change, -1, y to x on the left, and +1 on the right. And there's not any blending from one into the other where it's close to something. It's always exactly -1 or +1. And if I pick moments that span that corner, that vertex, I'm going to get something in between +1 and -1, but I can never make the graph look like a straight line by, zooming in. It's always going to have a corner in the center of it. There's other sorts of things other than that, like those sorts of rational power graphs that have cusps in them like this, or like some sorts of sine squared or absolute value of sine functions. They have these sort of curved things that go to a point. But there's also graphs that are really a big mess. And there's a section in your graph on them. I think this is something like infinitely wrinkly graphs or something like that is the title of it. Don't worry about the equations in there. We're not going to run into them because those are examples of things that don't have constant rates of change anywhere. Things like fractals. The equation for fractal curves, the closer you zoom in, the more details you see. So it never looks like a straight line. It always looks like, oh, there's more of the same little snowflakes or triangles or whatever sort of boundary shape it is. But in any case then, let's see, going back onto this, rate of change in a moment is what we're going to be looking at. So this is what I was talking about. Up until now, we've said that dx represents a small variation in x, but in the examples that we were using, it could have really been anything, whether it's adding a gallon of water to the barrel or 17 gallons of water to the barrel. It would change the weight by 8.3 times as many gallons, pounds in weight. Or whatever, when we were talking about the flag ceremony and raising and lowering the flags during the interval where there's this constant rate, which wasn't an extremely small interval, it just didn't include the very first seconds in the last interval we did. We could have used any amount of variation within the domain of x and it would have been perfectly okay. But we're going to be talking about a more general usage of this dx. It applies in all cases to anything except for those weirdest fractal functions, where if I zoom in close enough, I can find constant rate of change. So we're going to use just dx to represent small variations in x. So when you see that, just think about a small variation in x, or a small increase or small decrease in x, whatever it is you want to do. Lots of times we just talk about increase because, like, especially if it's time, we think about going forward, but you can also decrease, go backward also. And then if you focus on letting that be small variations in x, we'll call it a differential in x. And differential just literally is talking about the difference between things. But if you have seen calculus books before, whether it's you've taken calculus before or you know other people that have, or you talk about differentiation is one of the main two operations that we do in calculus. And differentiation comes from the same idea as this. It's finding the differences, but only over small intervals at a time. A derivative function is one that's derived from another function, and it represents the differentials throughout all the values of, all the legal values of x in that function, the domain of that function. So all these words seem kind of bizarre vocabulary, but this differential in x is talking about difference, change in x. All right, so if you have a constant rate of change relationship over small intervals, or an essentially constant rate of change relationship over small intervals, then we can use our constant rate of change relationships also. So if I know a differential in x, a small difference in x values, I can figure out the corresponding differential in y, dy. So within a moment, we're going to have a constant multiple that we're allowed to find dy based on knowing dx. And that sounds like, well, I only get to use it once though. So the idea is, if you think about what we're doing with Usain Bolt, maybe that 3.9 to 4.1 seconds, the rate of change in that moment was about 11.45, that's what it was. So whether I think about starting at time 3.9 and going all the way forward by 0.2 seconds, or talk about any interval within that 0.2 seconds, I can find the increase in distance from the start by taking the amount of time traveled and multiply by 11.45. It doesn't have to be just from time 3.9 using the whole interval to 4.1. Talking about any interval of time within that moment, I can use the same constant rate of change, 11.45, within that moment. So thinking about this is just the whole domain is this 3.9 to 4.1 were the legal x values where I'm allowed to use this constant rate of 11.45 meters per second. So it's not that we just get to use the number once and then we're done with it. It's that you can use this number within small moments for any smaller interval, whether it starts at the beginning and goes to the end, starts somewhere in the middle and goes a little bit forward. You can even use it to go backward. Now going backward in time sounds weird, but you could also talk about, well, if it was 0.05 seconds ago, how much closer was he to the starting line than he is now? Something like that. So you can always make up reasons to go backward even in time that doesn't involve time travel. But lots of times it does make it's easier sense to make of having dx being either positive or negative, but it does represent a small change in this independent quantity. All right, so let me move this guy right here to someplace else. All right, so function f, this is what we saw in the graph, represents Usain's distance from the starting line, and y is the dependent variable, x, or t, I guess I'm using x now. X is the number of seconds, y is the dependent variable, is distance from the start in meters, and f is the name of the function that relates the two. And let's see, so here's the full graph. I don't know if you can see this little, not the full graph, but this is from 0 to 1.5 seconds. But if you can see this little mark here, right around 1 second, this is zoomed in around that mark. So this is 1 second, this goes back to 0.99 seconds and up to, well, a little bit past 1.01 seconds. So this is 2/100ths of a second represented in the right-hand graph here, as opposed to the first graph we can see 1.5 seconds. So looking at this first graph, this is slightly zoomed in from what we saw earlier. I can tell for sure that over those first 1.5 seconds, he's not traveling at a constant rate, because it certainly looks very curved to me. So I wouldn't want to pick one number and assign it to that whole interval of 1-point-something seconds. But if I'm looking right around 1 second into the race, if I wanted to estimate his speed, all I have to do is look a little bit closer and find something that seems approximately linear. Maybe I can check a few different intervals to see. But if I had some data points here, and this is just a picture of GC, so I can't click on this one, but this looks approximately linear. So if I use the data from this zoomed in right around time 1, or this is a moment including 1 second into the race, I should be able to get something as close to that number I said earlier, like 6-point-something meters per second. So in order to find a speed, though, I can't just look at a single spot on that graph and kind of guess. I'd want to look at how as x changes a little bit within this moment, within this point, this very small domain, this like 2/100th of a second, 0.02 seconds from left to right. So I'm looking at a change within that moment, making, and this ratio of dx, the horizontal segment that's growing, to dy, the vertical segment that's growing, that should be approximately constant as I go a little bit through this. Now if I go too far, I'll notice more change. I'll notice a different ratio. But if we actually do this and find some numbers using GC or whatever, we can do some computations and find a number that would seem to represent the speed around time 1, or within the moment, including 1 second into the race. And there's no reason this has to start at 1 and go forward from there. It could start to the left of that and go to the right of it. But if I want to estimate the speed at time 1, I probably wouldn't just look over here, even though it's probably similar. I probably wouldn't look around here. I want to do something that involves this, but this just particular choice for this demonstration is, well, let's go forward a little bit in time from time 1 second. So let's take a look at, let me scoot this again. There's a bunch of things in this table here, but I want to make sure we understand what the symbols for them are, and also for the specific example, the value that we'd associate with them. So looking at this idea here, we're looking at Usain Bolt running, and we're looking about 1 second into the race. Based on this diagram that was moving to the right with the arrows there, I want to talk about the initial value of the independent variable, the initial value of the dependent variable, the differential in x, the differential in y, and the moment that we're talking about. Let me scoot this a little, I'm going to put this down on here. Nothing's happening down on that. So imagine that x varies from 1 second to 1.006 seconds. That's what was going on in this right here. So the largest it got was from this 1 second to 1.006 seconds. If we let x vary from 1 to 1.006, the y value varies from this value, a little bit less than 3.5, up to a little bit more than 3.5. And it shows here, it goes from 3.4882 to 3.5251. So thinking about this situation and how this is just an example of how we could compute his speed in this moment, or a speed that we're going to assign to 1 second into the race. Think about the values and then symbols that we also associate with each of these 6 things listed. I'll give you a couple minutes to think about this, discuss with a neighbor, etc. We'll go over these together. But just for this specific situation that's pictured below, there's a variety of ways you could do this on your own. You come up with similar results. Let me move this cursor off with that. All right, so if we are trying to do this computation of a rate of change for the moment x equals 1 second into the race, and we're doing this by imagining x varying from 1 second to 1.006 seconds, what is the initial value of the independent variable that we're using for this example? 1, right? It's just 1, x equals 1, or x initial, right? So let me get this to come back up again. All right. So it's 1 second. That's x initial. The initial value of the dependent variable. Initial value dependent variable. So that's the starting position, or y value. That one, right? 3.4882, which is the number of meters, but that's the initial value of y. The differential in x that we used, we could have chosen a lot of things. We could have chosen a lot of initial y and xy values also. But the differential that we're using is, well, let's see. We let x vary from 1 second to 1.006 seconds. So the dx value that we're using is 0.006. All right, x final minus x initial. So that number of seconds has gone by, 6/1000 of a second. The differential in y is the corresponding variation in distance that happens during this time, which is not quite as easy to subtract. Let's see, 251 and 118, 369. Maybe. Is that right? Maybe. Just trying to find the difference between these. Oh, am I missing is 0.0369. There we go. So I went 0.0369 meters during this 0.006 seconds. So during 6/1000 of a second, went 3.7 hundredths of a meter. Yeah, so this is 3 centimeters or something that he traveled, almost 4 centimeters during 6/1000 of a second. So that's pretty fast. There's not a symbol for the moment, but again, all the moment is the interval that we're thinking of where it seems that there's a constant rate of change. So you can say, oh, it's about 0.995 or 1.05 or something, but just this whole picture here, I can imagine this zoomed in graph to represent the moment that we're talking about. So there's not really a symbol for it, but if I wanted to describe what moment it is, I could talk about the domain of the function, the subset of the domain that we're showing. So this is x between, I'm just going to use interval notation here, about 0.995, or what was the left number? 0.99, got my thing in the way here. 0.99. Through 1.01. There's not a symbol for it. But the rate of change in the moment. Well, since we have in this picture listed one example of a corresponding variation in x and variation in y, the changes that correspond for time and distance during this picture shown. Well, if I want to find the rate of change, I want to know dy over dx, the ratio there, to find this m. It's that constant rate of change that we're looking for. And it's not constant all the time, but it's within this moment. We'll say, well, it's approximately constant. So we can call it m, we can call it dy over dx, but we'd need to compute it by finding this ratio dy over dx. So this 0.0369 meters in 0.006 seconds, which maybe about 5-ish meters per second. Let's see, a little bit less than 5 meters per second, just guessing. But you could do this division and get a result. And that's all we'd be looking for. It gives us a single number that doesn't correspond to a single spot on the graph. It corresponds to this region on the graph. Because in order to have change, a rate of change, we have to have some change. So it has to really apply to a small section, but you can make it as small as you want. I say, well, I'm going to assign that time to time 1, but it really is about the same if or that speed to time 1, but it's really about the same if I do anything within this moment. I can use this same speed, however this works out as a more normal looking number. I can assign that speed to any time within this moment here and saying during this moment he was traveling at about, I'm just going to say 5, at about 5 meters per second, whatever this divides out to be. It's that ratio of distance to time. So if I were to use slightly different numbers, I'd probably get a slightly different result, but it should be very near to 5 because this is a fairly small moment and it's a human, so thinking about tolerance level, he's not going to be able to change his speed drastically much quicker, and he's one of the fastest sort of human people. So even he can't change fast enough to make this look curved at this level of zooming. All right, so I'm going to stop at that for today. We'll pick up, we'll do another example. It's a little bit early today. We'll do another example like this at the start of class just to kind of review this process, and then we're going to work on Thursday on doing some actual computation. So make sure you have laptop with you. Just we'll use GC. We'll have a graph where you can click and zoom, and we'll even write formulas so it pre-calculates things for you. You don't have to write a second line and do subtraction and division. It'll just be done.
I got a question
Mm-hmm.
about